Hi, this video is a part of Machine Learning from Scratch playlist. In this playlist, I explain different machine learning algorithms implemented from scratch using Python. You can download the relevant Python files from the link given in the description of each video. Note that I do not code along, rather I make use of pen for explaining the tricky parts of code so that you people can read the notebooks and Python files and understand them yourself and of course re-implement them yourself. I'm expecting my audience to be well versed with machine learning general understanding, and they just need little hints for implementation of algorithms from scratch. As I have already explained binary decision trees implementation from scratch in the previous video, the link will be given in the description. In this video, what I want is to extend that idea, and what we will be doing is to fight the overfitting in decision tree by introducing two new early stopping conditions. One is the minimum node size and the second one is the minimum error reduction, which I'll be explaining in a bit. So binary decision tree classification has already been explained, where we talked about transforming into binary feature, creating subset of data based on the best feature, and best feature was selected based on the least classification error, and we recursively do it unless some conditions are met for stopping this recursion, which were creating leaf node if classification error is 0, or no feature is remained to split on, or we have reached the maximum depth. Now we want to introduce in this video these further two stopping conditions. One is the minimum node size, where we want to look at the data points in the node or subset of data, and based on some value, if the number of data points are below that value, below that number, so we want to stop the depth, stop the recursion, and we want to create that node a leaf node. And the same way we'll look at the error reduction, error before split minus error after split. If the reduction is less than some value, so we want to stop the recursion because we don't want to overfit. And at the prediction time, I have already explained in the previous video that how we follow the best features selected one after the another recursively to reach leaf node. And at leaf node, whatever the predicted value is, that will be the predicted value for that sample. So I think so this is really simple. This whole process is simple. Let me explain it in notebook. Okay, so we have already discussed this important theory create, which is a combination of scikit-learn and pandas. This lending club dataset where we have to predict whether loans are safe or not. We convert it into binary features, and we subsample it to make it balanced. The classes, the positive and negative classes, are balanced. Okay, so after converting it to categorical features, we have values of features either 0 or 1. This conversion can be done using any method, so we have done it using theory create and Python internal functions, but you can do it in any method, with any method you want. That is not an important part. The important part starts from basically creating decision tree function. Okay, but before that, I just want to explain the new conditions which were reaching the minimum node size. So in that, what we want to look at is that for at each node we have subset of data. We want to look at that subset of data length. If that length of subset of data is less than equal to minimum node size, so what we say is that we have reached the minimum node size. So if that condition is true, so we will stop the creation of tree further. And we have also introduced this new stopping condition, error reduction, where we will be looking at the error change, error before split minus error after split, and based on that condition we will also again stop the creation of tree recursively. Now all of these functions we have already explained in previous video. So this is like finding out the number of mistakes in any node, total number of mistakes in any node. And this is the function for finding best splitting feature. For each feature, we look at the subsample data, and samples where the value is 0, that goes to the left side of the tree. Values having value of 1 goes to the right side of the tree. And then we calculate the mistakes in left node and calculate the mistakes in right node. We look at the error, and if the error is less than best error, we keep track of that feature because that would be the best feature. In that way, we find out the best feature. Then we create leaf node. We have already discussed these 5 different key value pairs for each node, and leaf node, all of these will be none except for is leaf equal to true and prediction value. And prediction value will be the maximum of the two classes, whether it be positive or negative. Now in decision tree create, all of the things are same except for the introduction of two new conditions. The starting with this first condition is same, where we want to look at the purity. If the mistakes are 0, it means we have reached the extreme purity. The node is extremely pure, so we create the leaf node. If there are no remaining features, again we create leaf node. If we have reached the maximum depth, we again create leaf node. This is the new condition where we want to look at the minimum node size for the subset of data in the node. If that has reached, so we again create leaf node and we stop the creation further. And if all of these conditions are not true, so what we do is we split based on the best feature. We look at the left subset of data having value 0 in that best splitting feature, we assign that to a left split. That will be a left side of a tree, and the same goes for right side of a tree having samples value equal to 1. Then we calculate the error before split, and then we calculate the error after split by looking at the left split by giving as an input left split target and right split target to the intermediate node number mistake function. So after calculating error after split and already having error before split, we look at the error reduction value. If error reduction value is less than equal to minimum error reduction, this is a threshold that we have given as an input. So what we do is we create leaf node based on that error reduction condition. Okay, so we remove the remaining feature, we print the information, and we recurse toward the left side and toward the right side of a tree. And finally, we return the three important information, which is a splitting feature for a node, the left tree, and the right tree. And of course, because this is not a leaf node, so its leaf condition will be false and prediction will be none. That both information will be added in the create leaf node function. Now we count nodes as we have already explained. If it is leaf, then 1. Otherwise, add 1 again and again by recursively going towards left side and towards right side. So this is how we build a tree with a maximum depth of 6. And there are different conditions that we are trying out, and then we make prediction. Again, the prediction function is really same. If it is leaf, then we return the prediction value, and if it is not leaf, we look at the value of data set splitting feature. If it is 0, then we go towards the left. If it is 1, we go towards the right. And this is how it works. We evaluate the model by applying the lambda function on each data point in the data set. On each sample point, we apply the function classify tree, x. So we predict for each sample point, and after prediction for all the points by applying that lambda function, we calculate the classification error. And then we look at we explore the effect of maximum depth, where we have maximum depth equal to 2, 6, and 4, and we look at the results, and if we look at the effect of minimum error. So again, the maximum depth is constant and the minimum error has been increased and decreased, and you will look at it. So this is something you need to explore, and you need to look at the results in the notebook. And we can also explore the effect of minimum node size here. Now, just as a rule of thumb, if the depth increases, so of course the overfitting increases. If the overfitting increases, so what happens is that the bias decreases and the overfitting increases with the depth. But if you look at the error reduction value, so if the error reduction value is low, so it means we are going towards more and more purity. So it means more and more the depth will be increased. So it means overfitting will be increased, of course. In the same way, if we look at the minimum node sample size, so if the lower the value of minimum node sample size, it means we are going towards more purity and we are going towards greater depth, so overfitting will be increased. So somehow this is like a general crux of it, a crux of the analysis. You can just find it out in the notebook. I think so it is clear now.